Hello students, let us continue our discussion on units and measurements. And today we shall continue towards the next topic. In the last session, we were discussing uh, about the different methods of measuring different ranges of different quantities, namely three quantities: length, mass, time. And all those three quantities has three range: large range, small range, and average range. All those 9 different ranges of different quantities requires different types of measurements, sometimes direct, sometimes indirect. We discussed about all of them in the last session, and in this session we shall move ahead for discussing few more important topics of units and measurements, which are accuracy, precision, and errors. See, whenever we measure any quantity, okay, this is about actual real measurements that we do in our daily life and in the laboratories. Real measurements, not some theoretical, not something which is directly taken from the book. We are discussing about real measurements that we do in the lab and in the daily life. So when we measure something, we always expect the measurement to be more accurate, isn't it? We don't want less accurate measurement. So we often listen to this word accurate. You need to be accurate, you need to be perfect kind of words, right? So accuracy is a word which is associated with measurements. So what is accuracy means? See, accuracy is the measurement which is or we can say how close a measurement is to the true value of the quantity. So for example, say you have if you have a toothpaste on which you already have the value written 100 gram, okay, a 100-gram toothpaste. Now 100 gram is the true quantity, true value, okay. True value is the fixed value, okay, fixed value which belongs to standard value, which can also be taken as standard value. Now that 100 gram is the true value of mass of the toothpaste, right? Now if I take that toothpaste and measure with different weighing scales in home or in lab, I can get different readings, right? So now accuracy is about how close a measured value is, how close a measured value is to the true value. So now, as I considering the same example that I gave, 100 gram is the mass of the given toothpaste, okay, and now this 100 gram is the true value, okay, it is fixed, it is standard value. If I measure the same 100 gram toothpaste using different weighing scales which I have, like one like a spring balance, okay, let me show you how the spring balance look like, okay. So this is the spring balance, okay, one like this, or like a beam balance which will look somewhat like this, okay. So this is the spring balance and this is the beam balance, okay. So we have so many scales to measure the mass. So using different measuring devices, we are expected to get different readings, okay. Not only different apparatus, even if I make use of same spring balance, but 2-3 of them, okay, the other spring balance, one more spring balance, I can get different readings, Okay, a small variation is always expected, isn't it? So using different methods, if I measure the mass of same toothpaste and if I get 1 or 2 gram in one of the spring balance or any other balance, and if I get say 95 gram in one and say 108 gram in the other, and the other shows say 99 gram, and let me take one more which will give me 101 gram. Okay, so these are the different measurements or different readings that we get by measuring the same toothpaste with different scales. Okay, different scales, different readings. Okay, these are actual measurements. Now, which one do you think among these readings is more accurate or most accurate? Okay, see, accuracy is about how close the value is. We have so many readings here, 102 gram, 95, 100 and so on. Out of all these readings, I can see 99 gram and 101 gram. Both 99 gram and 101 gram are closest to this 100 gram value, isn't it? So both this and this readings, both of these are the most accurate readings or measurements I can call for the given true value. Okay, this is the true value and hence these two readings are taken to be most accurate. Okay, how close the value is to the true value, that is about accuracy of the measurement. Now often we can get confused between this accuracy and precision. See, precision is different, accuracy is different. Accuracy, we got to know how close the value is. Precision is not like so. Precision is how well the reading or the measurement is resoluted, or how well the resolution of the reading is. What do you mean by resolution? Okay, we'll see what is that resolution. Okay, so it's about precision. Precision is how well is the resolution. In precision, we look for this, how well the resolution of the measurement is. See, we do not worry about how close the value is to the true value. We don't bother about this when it comes to precision. When I say which value is most precise, which reading, which measurement has got more precision, then I look for number of decimals or number of digits that a reading contain. Okay, for example, say I have 3-4 readings as such. Okay, once again let me take the same example of 100 gram soap or 100 gram toothpaste measured with different kind of quantities or different kind of scales, giving us different measurements. Say one of the measurement that I get is again 102 gram, and one more measurement that I get is 95.5 gram. Okay, 0.5 gram. This can be obtained using say electronic scales and all. Okay, we can get it. And the other reading is say 105.5 gram. And one more reading, say the same two readings, 99 gram and 101 gram. So now among all these measurements, all these readings, if I ask you which is the most precise reading, okay, if I ask you which is the most precise reading, see, precision is about how well the reading is, how well resoluted, means how many decimal points are we considering, or what is the least value that can be measured using the kind of measurement that we do. See, when I take this regular spring balance, okay, see, as you can see here, I can measure 10 gram, 20 gram, 30, 40, 50, 90 and 100. I cannot measure 95 gram using this scale, okay, because it is designed as such. After 50, the next reading itself is 60, okay, the smallest reading. There is no 55 gram placed here. Similarly, I can get 90, but I cannot have 100, I cannot have 95 gram. Directly after 90, it goes to 100 gram, okay. If you consider the scale, the regular scale that you make use of, normally there is millimeters inside centimeters. So you can have 1 millimeter, 2 millimeter, okay, 1, 2, 3, 4, 5 millimeters. But you cannot have, normally in the regular scale, you will not have 1.5 millimeter or 0.5 millimeter. No, the reading will not be there. So that kind of reading with less resolution is considered to be less precise, and the reading with good resolution, with good number of digits, more number of digits, is considered to be more precise. So now you decide which one among these readings, or which readings among these are more precise or most precise. Look at this. Again, for 100 gram, 99 gram and 101 gram are close, very close to 100 gram, but they are accurate. Yes, they are accurate, but they are not precise. Okay, compared to these three readings, 95.5 and 105 gram are more precise. So the precision is more for this, because we have the reading giving up to 95.5 gram, okay. A decimal place is introduced here, okay. We have one decimal point, decimal place. So we can get the reading till 95.1, 95.2, 95.3 like that. You don't have such readings here, right? It's only 99 gram fixed, 101 gram fixed. So here it is 95.5, 105.5. So these two are more precise compared to the others. So the precision is about how well the reading, how well the resolution of the measurement is. So now if I have one more reading, say using electronic scale, I get the reading like 90.156, okay, 90.156. In such a situation, if all these readings are compared to get the most precise reading, 90.156 itself is the most precise compared to all this, because the precision is up to third decimal point, isn't it? Third decimal place, first, second, third. So till third decimal place we have the precision for the given measurement. So this is about accuracy and precision. Accuracy is how close is the measured value to the true value. Precision is about how well the measurement, or how well is the resolution of the measurement is, okay. So this is the most precise, and these two are the most accurate. Clear? Say I have one more reading, 99.5, okay. If I have one more reading, 99.5 gram, in such a situation, this itself is most accurate, at the same time most precise compared to all this, isn't it? Because 99.5 is the closest value, so it became accurate. At the same time, 99.5 has got one decimal place, and none of the readings here has got any decimal place. So this itself is most accurate because it is closest. This itself is most precise because it has more decimal places compared to this. Okay, the resolution is good. Okay, you are looking clearly. The reading is more clear or resoluted. So that itself is precision. Okay, how well the resolution is. Okay, 99.5 itself is most precise, most accurate if we have such a reading among these. Okay, if I have this, again this is most precise, this is most accurate, this is most precise. If I put all these readings together, okay, if I put all these readings together, this is most accurate, this is most precise. Clear? Okay, that's about accuracy and precision of measurement. And now we shall go for errors. So next is about errors. See, whenever we measure something, okay, there and all we can get errors. Okay, errors are always expected. They are of different kinds and different sources of error are there. But we do get errors when we measure, isn't it? You might be feeling like if you go to a vegetable shop or a provision store, there you might see if the seller is measuring something, you sometimes feel like if I measure that, the measurement would be more precise or more accurate, isn't it? If I measure instead of him, the measurement would be more accurate. Or I'll introduce the error when I measure will be very much lesser. Okay, you might be thinking in those kind of situation like that. So now we'll understand what is error and different types of error, different sources of error. Error is always expected whenever we measure. Okay, what is error then? Error is the uncertainty. Okay, nothing is 100% certain when we measure something, right? So there is nothing like 100% certain, because say if you measure the mass of say a certain rice, okay, then you say it is 1 kg, it is measured as 1 kg in a regular provision store. So the reading it can give is 1.5 something like 1.02 kg. That's how it can give, right? 1.02 kg in the regular provision store. Sometimes yes, it can also give 1.023 kg, right? But if you take the same rice and measure it using a very accurate, very precise instrument, then we see that it can also give like 1.025831 so on. So the reading can never be 100% perfect or certain. So there is always uncertainty in the measurement of any physical quantity using any instrument. That uncertain part of any measurement itself is considered as error. Okay, so error is the uncertainty in the measurement of a physical quantity using an instrument or using any instrument. Okay, you can make use of any kind of instrument, you will always get errors, right? Now these errors that we see are broadly classified as systematic error and random errors. Okay, so the types of errors are, one is systematic error, and the next is random error. Okay, these are the two types of error. Yeah, we'll get to know what exactly systematic error is, how do we get systematic error, and what is this random error, how do we get random error. We'll discuss all those things. But in the first place, which kind of errors are considered to be systematic error? See, if the error propagates in both the directions, which means sometimes the reading might get more than the actual reading, lesser than the actual reading. So the error can propagate in both the direction. Okay, if that is the kind of situation, okay, if the error propagates in both positive and negative direction, then those errors are considered to be random errors. Okay. Then we have systematic error here. So exactly the opposite. If the error propagates in one direction, either positive or negative, then the error is considered to be systematic error. Okay, this is the basic definition of systematic error and random errors. And now we'll see what are the different sources for systematic error, when or what are the different situations or conditions in which we get systematic error and random errors. First we shall take systematic error and understand or see what are the different sources for systematic error. Okay, we'll see the sources of systematic errors now. Right. So now we shall see different sources of systematic error. Majorly, we have three sources for systematic error. The first source is instrumental error. Obviously, whenever we measure something, the measuring instrument must be a perfect one, right? If the measuring device we are using is damaged, or it has imperfect design or imperfect calibration, then we will get error in the reading, isn't it? So the error due to the damage error due to the damage, imperfect design, and imperfect calibration. Calibration means see we have if you have 100 meters 100 centimeter scale. See, before you actually put the readings on that, it was just a stick of wood, isn't it? Nothing else. Then you made the readings. One using some technique, one actually printed the readings on top of it. So that itself is calibration. Okay, giving the or designing it or calibrating it somewhat close, but that is what is calibrating. Yes, this stick is 1 meter. That is done using another instrument, right? So that requires precise design. So imperfect design and imperfect calibration is called instrumental error. Okay. So as an example, say if you are asked to measure the length of say a wire or length of a classroom, anything like that, then you would require a tape or a meter scale like this, and the meter scale must be perfectly designed, perfectly calibrated, and it should not be damaged. Say I give you this meter scale and ask to measure the length, then you would be fine. Okay, the systematic error cannot be expected. If I have a broken scale, okay, if I break this scale somehow, if the scale got broke, then if I give you that broken scale and ask you to measure something, then obviously you will expect certain error in the measurement, isn't it? The measurement won't be accurate due to the damage that has occurred to the measuring device, the scale. You will get the error in the reading. So that kind of error is considered to be instrumental, okay, instrumental error. The example for that is error in measuring length with a damaged or broken with a broken scale, right? Sometimes the scale might be well calibrated, well designed, and no damage in it. Even then, if you yeah you might be very familiar with this kind of example. So when you take a new scale, the plastic scale, the transparent one that you see, the regular 15 centimeter scale, when the scale is new, you can see the readings very well on it, right? But as the time passes, the readings on the scale starts to go away, right? So that due to the scratches and all, it goes off, it weighs off. So now after certain time, the readings won't be that clear. They are not much visible clearly as the new scale. So due to that imperfect, due to that damage that has happened to the scale, it's a damage due to the scratches, it has happened. So due to the damage happened to the scale, now the readings that you get from that scale will have error because of the damage, and that kind of error is can also be considered as instrumental error. Clear with this? So this is about instrumental error, which is a source of systematic error, right? Now we shall see the next source of error. So the next error is imperfection in the measuring technique. Okay. So the second source of systematic error is imperfection in measuring, or it can also be considered as experimental. If it is more lab oriented thing, measurement, then we call it as experimental. Okay, measuring or experimental technique. So imperfection measuring or experimental technique is another source of systematic error. Now, what kind of error is this? Say, now if I ask you to check your weight using weighing scale, the regular weighing scale, then what you do? You stand on the weighing scale properly with the closed feet, okay, and you check for your weight, right? Now, say if the scale is perfect, it is well calibrated, well designed, and has no damage in it. So the scale is perfect, it will show you the perfect weight. But when you go for measuring using that perfect scale, anyhow it doesn't have any it don't doesn't have any has any systematic error, isn't it? Because the systematic error is eliminated by choosing a perfect instrument. So now the instrument is perfect, the instrumental error is eliminated, which means it can show the perfect reading. But the technique using which you measure must also be perfect, isn't it? If not, then obviously we can expect the error again. Just like if you make your friend stand beside you and just put your hand on top of his shoulder like this, and then you try to measure your weight, then you check. Okay, see, in the first technique or in the first way of measurement, you were following the rule properly, isn't it? So, or we can say they are the two different methods, okay, two different techniques that a person used to measure the weight. The first technique is he simply stood alone without any support. In the second technique, he just took a support and looked at the weight. So both the techniques, excuse me, So both the techniques are for measuring the weight, but the second technique will obviously give you error because it is imperfect, isn't it? Because when you take a support, part of your weight is going onto the support and only a part is going onto the scale. So you will not get the perfect reading, which means you will get the error. So that is about imperfection in measuring or experimental technique is. This itself is the error, no need of any explanation and all, but I can give you the example for this. Imperfection in measuring or experimental technique, the example is as follows. Okay, the standard example is different, but I want to give a different example. Okay, error in measuring weight of a person with the person taking support externally or taking support externally is fine. Externally will introduce this error, and that kind of error can be considered as error due to the imperfection in measuring or experimental technique. The other example that we see, the standard example, is measuring the temperature. Okay, so how do one measure the temperature? Yes, we now has got thermal scanners, but before we have thermal scanners, the standard device that was used to measure temperature was this thermometer, the regular mercury based thermometer, isn't it? The thermometer used to show the temperature of the body. Normally, where do one keep the thermometer? Thermometer is kept under the armpit here, right? So here we'll keep the thermometer and see the temperature of the body. So this technique has error in it. It's an imperfect technique, isn't it? Because the temperature at certain part of the body is not going to be same throughout the body, isn't it? So this technique of measuring temperature of the body by keeping the thermometer under the armpit is a technique which involves which itself is imperfect. Okay, which is an imperfect technique, and hence the error is expected in that kind of measurement, and that error comes under imperfection in measuring or experimental technique. Clear? So these are the few examples of the second source of systematic error. Okay, now let me take the third source here itself. The third source and the last source of systematic error is personal error. What are these personal errors? So these personal errors are obtained due to the individual bias. What is individual bias? Bias means, see, if I see certain reading, this might have happened between you and your friend. In certain readings, when you measure the length of a line, okay, you might see it like, okay, the reading is 5.5 centimeter, but your friend sees the same reading and says, no, it is not 5.5, it is 5.6. And one more friend sees the same reading, observes it and says, it's not 5.5 and 5.6, it's actually 5.4. So why is this error happening? The instrumental device is perfect. The technique used is also perfect. You are all doing everything perfectly. There is no error in the instrument. Instrument is fine. Measuring technique is also fine. But depending on the observer, who is observing the measurement, there also differs the readings. Okay, if you observe the measurement, the reading might be different. If your friend observes it, the reading might be something else, isn't it? And this can also be observed when you have balancing or like a beam balance. When we have the beam balance, then someone says no, it is balanced at this position. Someone might say no, it is not still balanced, it is still oscillating, we just cannot say it is balanced. So personal bias, okay, it is not about the technique, it's not about the device, it's about the individual person who is observing. Due to the person who observes the reading, there might be an error, and this error can also be obtained if the person has any physical disabilities like visual problem. See, if a person has vision problem, then the reading he observes might differ, might be of error when we compare to a person with without any visual disabilities, right? So that is about personal error, and this personal error is due to the individual bias. Okay, so the error in the measurement, due to the individual bias, due to the individual bias is considered to be personal error. Okay, see, and not sure whether you have observed this kind of reading or not. See, uh, when you observe something, if you have observed ammeters and voltmeters in, if you had observed them in the previous classes, their parallax plays the role. Okay, if you observe the needle of the ammeter or voltmeter, let me bring them. Okay, I'll show you how does an ammeter and voltmeter look like, or a galvanometer. See, now I have an instrument which is galvanometer. Okay, it's a galvanometer. So it has an observer, a needle here in the center here. Okay, so if I observe this needle by closing my right eye, the reading that I see is different, and if I close my left eye and observe, the reading that I see is different. Okay, little different, very little value is varied by observing the reading with one eye closed, right? So now a person's right eye might be dominated, he might be looking at the reading like this. Okay, if the person's, you can see this. Okay, try to observe. See, if now the reading is perfect, it is 0. Okay, now if you observe the same reading like this, now it's not 0, isn't it? And like this, it's not 0 again, it's some positive value, and if you go here, it is some negative value. See, the instrument is perfect, measuring technique is perfect, but the observer, where the observer is standing, how good the eyes of the observer are, all those things matters. So depending on all those things, we get this personal error. The example for personal error is, say, what is this effect? From right eye we got some reading, from left eye alone we got some other reading. This effect itself is parallax effect, isn't it? So example is the error due to parallax. Okay, so error due to parallax can be considered as personal error. Clear with this? So this personal error can be obtained even if we have something like a single, if a single person himself is measuring with right eye closed once and left eye closed the other time, even then he can observe different readings, and that kind of error is considered to be personal error. Okay, so now this is about 3 different sources of systematic error, and we'll move ahead now. Yeah, and now we'll see a funny video, okay, in which a person tries to measure the mass, and you try to tell me what kind of error is involved in that measurement. Okay. So as you saw, the person was struggling to measure. The error involved, you might think, is it's the personal error, isn't it? Because the person measuring is not using it properly, the device properly. No, it is not the personal error, it is the imperfection in the experimental technique, isn't it? Person's eyes are proper, they are not affecting the reading. The person who is measuring does not have any disability, or there are no two persons, there is only one person who is measuring it, but the technique which he is using to measure is imperfect, it's not right, that is why he is getting that error, isn't it? So that is about the difference between the actual difference between personal and the imperfect and imperfection in the experimental technique kind of errors. Now we shall go for the random errors. See, random errors involves various sources. Okay, we'll just take the sources directly. But mainly, random errors arise due to the unexpected factors that occurs during the measurement. For example, say you are measuring the mass of say a delicate mass, a small mass using weighing pans. Okay, like one you see here. Okay, let me show you them. See, here you have two beam balances. Okay, it's not set, but that one is set. Okay, if you can observe them, this beam balances has got close covering from all the sides. Okay, and we need to open the doors, keep the weights, and then we need to measure. Why is this delicate setup is there for this kind of device? The reason being, if we have wind blowing, the measurement that we are doing is so delicate, mere the blow of wind will alter the reading, isn't it? In the same way, even if the measurements are of large scale, say we are just say you are measuring your weight by standing on the weighing scale. Okay, so there what happens is you stand at the weighing scale, you put the coin. But suddenly what happens, some of your say mischievous friend comes and pushes you. You are pushed like this, but the coin is just inserted. The reading that you get, the measurement that you get of your weight will be of certain error, isn't it? Because there some random person or random situation arised due to which everything was perfect, no instrumental error, no personal error, no error due to the imperfection in technique, everything was perfect, but some random situation arose or came, and hence the reading was disturbed, the measurement was disturbed. So that kind of unexpected factors affecting the measurements will cause random errors. Okay, so what are random errors? Errors due to unexpected factors affecting the measurement are considered to be random errors. Okay, so like variation in the voltage, if we are doing some electrical experiment, if the voltage in the circuit varies abruptly, or the power supply, the voltage of the power supply varies abruptly, then we can expect error in the reading. Variation or the measurement error due to the blow of wind or any other factors that arise unexpectedly comes under random errors. Okay, that is about random error. And finally, we have one major source of error. Okay, one of the source of error which can come in both random and systematic error. Okay, that error which can come in both random and systematic error is called least count error. Okay, first of all, least count, which means how much least value a measuring device can measure or count. So, okay, the least value. See, if I have this scale, okay, this scale is of same least count as of your regular scale. See, in between 1 centimeter and 2 centimeters, I have millimeters again. So, I can count 0.1 centimeter, which is the least possible count using this scale. Okay, so 0.1 centimeter is the least count of this scale. Even if you take take your regular scale of 15 centimeter one, the plastic scale, even in that the measurement will be the least count will be 0.1 centimeter itself, isn't it? 0.1 centimeter is the least possible count, because you cannot count beyond that. 0.1, okay, say this is 1 centimeter, this is 2 centimeter, between them you will have 1 2 3 4 5 6 7 8 9 10. So this is 1 millimeter, right, or 0.1 centimeter. So 1 millimeter is the least count of this scale, isn't it? The how less how less a reading can be taken using a given instrument. Okay, that is about least count. Least count, that is what is least count. And now if you have two instruments, two scales, one which again has readings inside 1 millimeter, one which do not have readings inside millimeter again. Out of these two scales, because you might see some other scales which look like this: 0, 1, 2, and you have 1, 2, 3, 4, 5, 1, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is one scale that you have, and you have one more scale, the same kind of scale, okay, but this time this scale has only this kind of reading, okay, 0, 0.5, 1, 1.5, 2. Where do you find this kind of readings or scale? Okay, if you have seen a measuring tape, the measuring tape will not have any millimeters inside it. Okay, the scale that I showed you, just the wooden scale that I showed you, has got millimeters in it, right? But look at this. When you take this measuring tape, yeah, even this measuring tape, this particular measuring tape has millimeters in it. This is a good measuring tape. Okay, 1, no, look at this. Yeah, if you can observe, see, this is 1, this is 2, between which you have only 4 readings: 1, 2, 3, 4. Okay, can you observe that between 1 and 2 you have only 4 divisions? So the reading is somewhat like this. For the tape, it is 0, 1, 2, 3, 4, 1, 2, 3, 4, 5, and you have 1, 2, 3, 4. So this is how the readings are in the measuring tape. But if you take the scale, in the scale you have 10 divisions between 1 and 2, isn't it? Between 1 and 2 you have 10 divisions. So when I take these two, and if I ask you to measure the reading of say length of a certain stick or any other thing using the tape, okay, then the reading that you can expect is say 1.5 2 centimeter. Yes, that reading can be taken. Or 1.6 centimeter, that can also be taken, because it is 1.2 can be taken, 1.4, 1.6, 1.8, 2. These are the readings which are possible in the tape. But when we have the scale, we can get the readings like 1.1, 1.2, 1.3. I can get all these readings. So the least count here is 1 millimeter. Okay, I can measure 1 millimeter using the scale, but the least count for the tape is not 1 millimeter, it is 2 millimeter, because the least value that I can measure is not 1 millimeter, instead it is 2 millimeter for the tape and it is 1 millimeter for the scale. So if I give you the tape and ask you to measure something, if the reading that you get is 1.2 centimeter, okay, say the reading comes and stands somewhere here, okay, if I ask you to measure something like this, the reading comes and stands here, which reading should you take? So it is 1 till here, 1.2, 1.4. So the reading is somewhere between 1.2 and 1.4. Some might think that, okay, let us take 1.4 or 1.2, or some of you might think let us take 1.3. No, you cannot take 1.3 because there is no reading mentioned in this scale as 1.3. So you cannot take that. All you can do is you can come back to 1.2. Okay, so 1.2 is the reading that you will write, 1.2 centimeter. But if the same object is taken here, okay, and is measured like this using the scale, then you get the exact reading of 1.3 centimeter. So now there is error in this reading due to the least count of the measuring device. The least count is 2 millimeter and hence the reading that we obtained is 1.2 centimeter. If I measure the same device or same object using the scale, the length that I get is 1.3 centimeter, right? And that 1.3 centimeter is more accurate, okay? And this has less error, okay, very less error compared to this, but this has more error because the instrument has more least count, okay? So lesser the least count, lesser the error. More the least count, more the error, okay? So depending on the instrument that we choose, okay, instrument is perfect, both of them are perfect instruments, there is no doubt in it, but the precision of the measurement is decided by the least count of the measuring device. Least count of measuring tape is 2 millimeter, least count of measuring this scale is 1 millimeter. So this reading is always preferable. Which one? The scale's reading is always preferable because it can give more precise reading. Precision is more because least count is less. Here precision is less because least count is more. Okay, clear on that? So that is the least count error. Error due to the least count of measuring device. Okay, error due to the least count of the measuring device is considered to be least count error. Okay, this least count error can be both in systematic and random depending on the situation. Okay, so that's about least count error. Thank you.